Next problem, the table shows the number of new branches in each figure of the pattern below. So from figure to figure, we have how many branches on this one? 3 branches. If you think of this like the trunk, then we have 3 branches here. How many branches here? 9 branches. How many branches here? Yeah, there's 3 on this one right here, and then there's 3 of those, so that's a total of 9. But then there's 3 of those branches for a total of 27. Okay? So we're just looking at the new branches, and that's why they've colored them red here. And that's what the table is showing me. Figure number is the thing that we are changing. Figure 1, 2, 3, and then we're supposed to figure out how many there would be on figure 4 and figure 5. So the number of new branches in figure 1 is 3, then 9, then 27. What would this one be? So you're seeing the pattern. We have 3 times 3 is 9, times 3 is 27, times 3 is 81. Is that right? So I'm not going to sit here and draw figure 4. That's a lot. What about figure 5? 81 times 3? 243. Lots and lots of little branches. Okay? So like I said, this is kind of like a fractal pattern here. We just keep branching out more and more and more. All right? The next one would have 3 times that. It's kind of a ridiculous amount. But we want to come up with, so we have, what is a pattern you can use to complete the table? We said each one of these is being multiplied by 3 each time. So represent the relationship using words, an equation, and a graph. So in words, what can we say? In words, so the next figure, let's do this. I'll just help you out with this part. The next figure has what? 3 times. 3 times what? Three times the previous number of new branches. So to get from figure 1 to figure 2, we have 3 times 3. To get from figure 2 to figure 3, we multiply it by 3. To get from figure 3 to figure 4, we multiply it by 3. And then times 3 again. And if we wanted to continue doing that, we'd just be multiplying by 3. We have a notation to do that. We have a way to show that we are multiplying by 3 a certain number of times. Exponent? Right? Yeah? But am I cubing it? Is this x cubed? Is it y equals x cubed? So if x is the figure number, then if I plug in figure 1, I better get 3 as my answer, right? So I plug in 1. 1 cubed is 1 times 1 times 1, which is 1. 2 cubed is 2 times 2 times 2, which is 8. 3 cubed is 3 times 3 times 3, which is 9. I'm not getting the right answer here, so this can't be the right equation. You're close, though. We can have an exponent here. But this would be 9 is 3 to the, like if I want 9, I get 3 times 3, which is 3 squared, right? If I want 27, then I have 3 times 3 times 3 to get to 27, right? So that would be 3 to the 3rd power. If I want 81, well, I had to get there by going 3 times 3 times 3 times 3, which is 3 to the 4th power. And then this one would be 3 to the 5th power. This one over here would be 3 to the 1st power. It's just 3. So what's the equation going to be? Y equals 3 to the x. Good. The exponent is the thing that's changing. So that means I have to have the variable in the exponent. And this is the first time you've seen something called an exponential function. We'll talk about those more, but this is your first kind of look at an exponential function. The variable is in the exponent here. The graph of an exponential function we're about to see. They all look very similar. So first I want to come up with my graph. I don't have any negative numbers here in this situation. So my origin in the lower left corner is still good. The number of figures, so figure number, goes on the x-axis. And then new branches on the y-axis. And then I can plot my points. No, I need a scale, don't I? So let me change my scale here. 1, 2, 3, 4, 5 by ones is fine on the x-axis. But then I got to get all the way to 243. I got 14 lines. Going by 2s would get me to 28. So if I go by 20s, that would get me to 280, which covers the 243. So I'm going to go by 20s. And then I'll mark those 20, 40, 60, 80, 100, 20, 40, 60, 80, 200, and then I can figure out the rest from there. So now I make that graph. We have 1, 3. I'm going by 20, so that's pretty low on that graph right there. Then I have 2, 9, so just about halfway. And then 3, 27, so here's 3, and then 27, there's 20. And then that would be 30 halfway, so I'm just going to back off a little bit and put my dot there. Then 4, 81, so I go to 4, and then 20, 40, 60, 80, and then 81 is just going to be slightly higher than 80. And then finally 5, 243, so 1, 2, 3, 4, 5, and then 100, 200, 220, 240, and then 243 just a little bit higher, right there. There's my graph. For exponential functions that we have right here, the graph is always going to look like this. It's going to kind of look like what I call a hockey stick graph. It goes off really, really fast. And there's a lot of really interesting mathematical things that we can do with exponential functions. They show up all over the place, like in nature or like populations and things like that. So this is sort of your introduction to very important pieces of mathematics right here. And it came from a fractal pattern. So all of this stuff really kind of gets tied together, and really the more you let your mind kind of accept these things and learn them, the faster you will understand mathematics. It's actually kind of an exciting time right now for you guys. A function is just a machine. Just keep that in mind. If you put something into a function, you're going to get something out of the function. So whether the function has a linear graph or a nonlinear graph, if the function looks like a line or some sort of curve, doesn't matter. The function can be represented by an equation. And that's kind of where we're headed. So we have a bunch of ordered pairs sitting here. We're told that those ordered pairs represent a function. Just by looking at those ordered pairs, how could I say if it is a function or not? No repeated x's. So there, and there. 1, 2, 3, 4, 5. I don't have any repeated x values. So I can kind of agree that this is a function, or at least it could be a function. All right. So they're telling me they represent a function. What is a rule that represents this function? So now I'm not given a table. I'm not given any sort of scenario with cool stuff like fractals going on. I need to make that table. There's no story behind it. You just make the table and see what you see. Okay? So it says make a table to organize the x and y values. For each row, identify rules that produce the given y value when you substitute the x value in, and then look for the pattern that in the y values. So you can decide what the rule is going to be. So let's make this table. We have x, we have y. We have 1, 2, and then 2, 4, and then 3, 8, and then 4, 16, and then 5, 32. So let's just come up with some ideas. It says, for each row, identify rules that produce the given y value when you substitute in the x value. Look for a pattern in the y values. Let's just come up with some thoughts here. What is going on? Squared? Okay. So let's write an equation. Y equals x squared. That's an option. Do we have any other options? You were thinking y equals x squared as well. Okay. Do we have any other thoughts? So look at this first one right here. What could I do to 1 to get to 2? I could square it. We could multiply by 2. So I could maybe have y equals 2x. How else could I get from 1 to 2? Add 1 to it. So I could have y equals x plus 1. Anything else I could do? No? Okay. So then we have some ideas of what could happen. So now we want to go on to the next one and see if any of these equations still work. So if I have x is 2, if I plug it into this top one here, do I get 4? Yes. So this one still could be right. If I plug 2 into this one, do I get 4? Yes. So this one still could be right. If I plug 2 into this one, do I get 4? No. So that one cannot be right. All right, go on to the next ordered pair. Take 3, plug it in. If I plug 3 in here, do I get 8? No, I get 9. So this can't be right. If I take 3 and I plug it in here, do I get 8? No. So this one can't be right either. There is something going on here, though. Take a look at the y values. We just tried to find patterns in the x value. It didn't do anything for us. So let's try to take a look for a pattern in the y values. We're just looking at y now. Look at those numbers. How could I go from here to here to here to here to here? Yeah. So you see that pattern right away. Each time 2 gets doubled, and then double it, and then double it, and then double it. Okay? So basically what I have here is 2 times 2 times 2 times 2 times 2, and so on. So the next one down would be 64, and then 128, and then 256, and those numbers. Into the thousands, yeah. Too much for us to worry about, right? Okay, so I need to come up with an equation that shows that happening. It's not x equals. It's still y equals. Huh? Y equals y squared? We have to have an x involved. It's still y equals. So look at this. How do I get to 4 if I'm multiplying by 2 each time? I need 2 squared. How do I get to 8 if I'm multiplying by 2 each time? I need 2 to the third. 2 times 2 times 2 gets me to 8. 2 times 2 times 2 times 2 gets me to 16. It's another exponential function. 2 to the x power, actually. So looking at the x to get to y didn't work for us. So then we looked for a pattern in the y. And once we found that pattern in the y, we just had to think about for a second, how can we get there? And it's this. 2 times 2 times 2 times however many 2's multiplied times each other. That means 2 to the x power. Another exponential function. So let's graph it. We have x and y. There's no negative numbers. It's just x and y, so there's no need to make some sort of story label for, sorry, that's a y. It's just x and y on our axes. We're going all the way to 32. I got 14 lines. Let's just go by 2's. And we'll be slightly off our graph, but I'm okay with that. So for 1, we have 2, which is there. For 2, we have 4, which is there. For 3, we have 8. Oops, not there. It's there. We're going by 2's. Sorry. For 3, we have 8, which is there. For 4, we have 16. So there's 8, 10, 12, 14, 16. And then for 5, we have 32. So there's 5. That's 16 right there. 18, 20, 22, 24, 26, 28. So I'm going to guess at 30 and then 32 being right there. It's another hockey stick looking graph. So we have this problem. What is a rule for the function represented by the ordered pairs that they're giving you here? This time we want to try to come up with an equation again. So what's the first thing we should do? Okay, so take a look to make sure that it is a function. It says, what is a rule for the function? So they're kind of telling me that it is. It's worth it to take a look at the ordered pairs, though, and see, do we have any repeated x values? No. All right, so we can kind of agree that that's probably a function. So, now what? Make a table, okay. So we have x and y, and what am I going to put in my table? 1, 1, and then 2, 4, and then, yeah, and then, okay, so now we want to look at how to go from x to y, and then maybe if that doesn't work, we look at the pattern in the y values. Yes? Y equals 2x? Is that what you're saying? Okay, let's try it. Y equals 2x. Y equals x squared, another idea. Anything else? No? Okay. So take this first order pair right here and plug it in. If I plug x in as 1, do I get 1 for y? 1 times 2 is 2. So no, I don't. That one doesn't work. If I plug 1 in for x, do I get 1 for y? Yes. If I plug 2 in for x, do I get 4 for y? All right. If I plug 3 in for x, do I get 9 for y? Yes. Is this the right pattern? Yeah, so this is the equation right here. Y equals x squared. And then if we're going to graph it, again, we don't have any ordered pairs that are negative here, so the origin can be sitting right here, x and y. I do have all the way up to 25, so I'm going to go by 2's here, just so I get everything on there. And then 1, 1, so there, and then 2, 4, so there, and then 3, 9, so that's 4, 6, 8, 9 is halfway, and then 4, 16, so 4, there's 10, 12, 14, 16, and then 5, 25. So there's 5, that's 16, 18, 20, 22, 24, 25. So there's your graph, another curve.